Good morning, guys, or afternoon, or whatever it is to you.
Hello?
Hi, can you hear me? No, probably not.
No, I can hear you well. Can you hear me?
Yep. So we're just waiting for Dennis real quick. Did you guys get the download that he sent out?
In the PDF file, right?
Yeah. I think I'm just the organizer. So I don't.
Hey, how you doing, everybody?
Hey,
Dennis.
Dennis. Just saying it's your show, so have at it.
Got the crew online. How's it going, Rob? Thank you so much for setting this up. I think Christina, Michael, and Sebastian are on, and Angelina. Hey, Angelina.
Hey, how are ya?
And I'm recording it, Dennis, to
Cool.
the extent that matters.
Great. Now I have to sound like I know what I'm talking about.
Hi, everyone.
Cool. So should I begin?
Yes, please.
All right. Sounds good. So did everyone get a chance to so I think basically with week one, the biggest challenge is trying to get through their crazy word questions and somehow understand how we extrapolate what we need to use the Bayes rule to give us an answer. So rather than try to go into some like huge, profound statistical understanding of what the Bayes rule is, I tried to break it down into more like a step-by-step approach of how to just break down the questions and get the information we need to plug into the Bayes rule and get us an answer. And so I find that when you just go step by step and keep everything really organized, for the Bayes rules questions, they actually can become manageable to answer. Unfortunately, it seems like in all of the questions, they also throw in like a little, I want to call it like a trick. And then it's also a bit annoying because the language of statistics is kind of close to like the English we normally speak, but the words sometimes mean something slightly different. So I feel like just a really formal step-by-step approach is the best way to tackle these questions. And so I tried to put that all of like the philosophy behind solving these questions into the Word document that I circulated. So after I kind of talked you through this, you're not left in the dark. There's some documentation of how to actually get through these questions. So I'm also doing courses right now in machine learning, and this is where like the Bayes rule is actually used a lot, because it's a really interesting tool in that a lot of times with machine learning, you have a bunch of data. It gives you like a probability, and then new stuff happens and you want to update that probability. So in that universe, it's a pretty useful little tool. So it's not just something that this professor invented to make our lives miserable. There's some real practical upside to this approach. I find it challenging because this initial probability of whether something will happen or not in the computer science world, there's a lot of data to support it. In these questions, he just kind of gives it to you. I don't know where he's getting those numbers from. I think that's part of the challenge of understanding these questions is that there's not a lot of supporting information as to where the initial probabilities come from, but whatever. So why don't I get on with talking about the equation? So basically, the Bayes rule equation is something that when you have probabilities that exist today, and then there's an event, you know those probabilities, and you know the impact of the event on those probabilities, and you can update them to get a better understanding of the world. That in a nutshell is the Bayes rule. What's cool about the Bayes rule is that those probabilities or the calculations of those can be quite simple, and then I'll let you do something really advanced, which will update your understanding of the world. So the challenging part is that, oh, sorry, someone's talking. Oh, it's Leo. Hey, Leo. So the challenging part, at least for me, when I read these questions, is that what happens is that you have probabilities of something happening in like a good state and a bad state. and then you have a probability you're in the good state or you're in the bad state. So it reminds me of that movie Inception, where the people are dreaming and then they dream inside the dream. It's hard to get your head to, because you're talking about probabilities and you're talking about probabilities of probabilities. That's super annoying. So I find the best way to do it is to just get everything down on a chart so that you can start to be organized and understand what we're talking about, and it becomes quite clear. So the whole approach really reflects just a methodology of how to put this into like a chart that's the same for every question. And then that chart lets you essentially solve the Bayes rule, which gives you the answer to the question. So that's kind of the background on both the Bayes rule and kind of why I developed this approach to solve these questions. I don't have a good statistics background, so this is very much like okay, here's a really practical way to try and get a hold of these questions, rather than spending the next year developing an intuitive statistics understanding of these questions. So, so let's begin. So as we just talked about, the Bayes rule is something where you have the state of the world, and then you have an event that updates the probabilities that you started with in the state of the world. So the first step is kind of to get organized and figure out what the state of the world is. And that, in this language of statistics, that's called the prior, or the prior probabilities. That's, I think, what the coursework talks about. So we'll keep consistent with the coursework. So our initial state of the world before the event is the prior. And so that's where my chart always starts. This is, if you're looking at the Word doc, this would be page 6 of the Word doc. So I start with a chart that basically, and I guess the other thing about this course is that regardless of like the fact that you can use the Bayes rule to do all sorts of things in machine learning, in this case, we're really talking about a good state and a bad state and some probabilities that are associated with that. So that is where we start with our chart. So if everyone's looking at page 6, I always start with a chart that says the good state, the bad state for the prior, and the probability that something happens, the probability that something doesn't happen. Juliana just asked for clarification which Excel we'll be using during the final exam. I have no idea. I have no idea. I have no idea. I don't know. Luckily for this.
If I may, sorry. So the teacher actually answered that. So we can use any Excel tool, whether it's the one that we've created personally, individually, or the one that he shared with us. So we can use any Excel file.
Amazing. So what I'll probably do then is I'm going to create an Excel file with this template that I use. And I'll just circulate that to everyone so that
and all the answers to the exam, right?
What's that?
You'll include all the answers to the exam in there as well?
If I could, I would.
Great suggestion.
Absolutely. If I knew the answers to the exam, I would absolutely. Exactly. I have a feeling the answers from the exam might be from some of the questions in the course, so I'd probably spend a bit of time learning each question in the course. That would be my approach to that. So, all right. So to get back to it, we start with the just getting our chart started so we can get organized. So we always start with the prior, and the good state, the bad state, the probability something will happen, and that's going to happen in the good state. The probability something will not happen in the good state. We also do that for the bad state. And then the probability that we're in the good state or the probability that we're in the bad state. Those are the first kind of things to get into the chart. So why don't we look at the first question from the quiz, which is, I have put it out in page 7 of the Word doc. And then we can just show how this flows into the chart. Okay. Recall the recharge-free cell phone example from the class. In the good state of the world, 60% of the customers will actually purchase your phone, whereas in the bad state, only 20% of your customers will purchase your phone. You consider now the good state and the bad state of the world to be equally likely. Now suppose you're at a text conference and you have 2 people, Meg and Maggie. One of them is very excited to hear about the phone and confirms they'll buy it. One of them won't. So what is your posterior probability about the good state of the world? That's really just a complicated way of asking. The posterior is just the updated probability. So how do we update our initial probabilities? So we know we're updating the probability, or we're looking for a posterior. We know this is the Bayes rule. So, okay. So now we have our chart, and let's go into the question now and see how we can update the chart. So there's a sentence that stands out. In the good state of the world, 60% of your customers will actually purchase your phone. So now we can go into our chart. Okay, so under good state, we know that there's a 60% chance, or we can use 0.6. And so if there's a 60% chance someone will buy, then that means that there's a 40% chance someone will not buy in the good state. So those are the first things we put into our chart, and we give ourselves a pat on the back because we're really getting somewhere now. Second sentence, whereas in the bad state of the world, only 20% of the customers will purchase your phone. This tells us that in the good state, in the bad state, 20% of the people will buy. So by that logic, 80% of the people will not buy, so we use 0.2 and 0.8. So now I'm on to page, I'm on to page 7 now. So, okay, so you consider the good state and the bad state to be equally likely. Okay, so if two things are equally likely, then there's a 50-50 chance, and that gives us now the probability of each state. So you have 50% chance it's in the good state, and 50% chance of the bad state. So if we use this format, the probability of state of the good state is actually one of the things we need for the Bayes rule. So it's really cool because if you need to know 3 things for to get the answer for the Bayes rule, then we've actually now got one of them. And so it's the probability of the good state, or the probability of the state of the good state. So awesome. So our chart's coming together, and now we actually have figured out one of the 3 things that we need to figure out to use the Bayes rule. And if you do the chart this way, it will always be in this place. Okay, great. So now we have now we have a full picture of the prior. So now we move on to what happens after the prior. Is now we have an event. This event is going to provide us some insight on how the prior gets updated. And so between the prior and the event, now we have all the information we need to use the Bayes rule. So let's move on and explore the event. Now, this question has like a real, I don't know, I want to call it a dirty trick, in that none of the coursework discusses the concept of having multiple events. But in this case, we have 2 events. And it's even trickier because they give us names of the people, Maggie and Meg. So it feels like Meg says yes and Maggie says no. But in reality, the way the question is worded, it says one of them is excited to hear about the phone and confirms they'd buy it, and one of them doesn't. And so we don't actually know if it's Maggie or Meg. We just know that one person does and one person doesn't. So we actually have to do a slightly more complicated calculation of the probability of this event in the good state and in the bad state, because we don't know if it's person A bought and person B didn't, or person B bought and person A didn't. So we have to calculate the probability of both. And that's probably where most people ran into a challenge with this question, is that they probably just assume that it meant Maggie bought, Meg didn't. We know what happened, and it's just one event, quote unquote. And so we calculate the probability, but you actually have to go through and look at the whole situation. Typically, that's done with like you do a little diagram, and you'll say, okay, you know, if Maggie bought and Meg bought, you know, there's a certain probability of that. If Maggie bought and Meg didn't, then there's a certain probability of that. And you look at all the different cases, and then you look at which ones match the information. And so that's why we actually have to do a bit of addition here. And so there's multiple events. And so I tried to explain that the best I could on the page in terms of how you actually calculate it and where those numbers come from. But it basically boils down to the events are that person A bought it and person B didn't, or person B bought it and person A didn't. So we sum the probabilities of those two events, and now we get a probability of what we observed happening in each state. So that's the probability of seeing this happen in the good state and the probability of seeing this happen in the bad state. And it's a bit of work to get there, but now that we did, it actually gives us the second piece of the equation we need to solve the Bayes rule. So which is the probability, the event in the good state. So now we're left with this final one, which is capital P at capital B bracket. So the way we get to this now that our chart is complete is that we always multiply the probability of state in the good state against the probability of the event happening in the good state, and the probability of being in the bad state with the probability of the event being this bad state. And so it's, if our chart is organized the way it is, then I pointed out at the little arrows of what you're adding and multiplying. And this gives us our P at B, which allows us then, we have the three components we need to solve the Bayes rule. And so the Bayes rule, as we looked at in the sort of practical example, it gives us your posterior probability. And so we started off with this idea that there's a 50-50 chance that we're in the good state or the bad state. And after doing a bit of work and organizing ourselves, all of our posterior and event into the chart, it allows us to use the Bayes rule. And the Bayes rule tells us that, okay, now that we saw this happen, that one person bought, one person didn't, we now know that it's actually a 60% chance. We've updated our probability as 50-50. So now there's a 60% chance we're in the good state. And by knowing that, we also know there's now 40% chance we're in the bad state. So we had an initial probability of state, which was 50-50. We saw an event. And then based on that event, we updated. And we now realize that it's not 50-50 anymore. It's 60-40. And so that also is, in a nutshell, how you look at question one of the quiz. Does that help? I have no idea. Is this helping anybody?
Yes, it is.
Yeah,
Okay.
I have to say it's awesome actually to have it in a breakdown, you know, because like it's hard to find an approach in the beginning. So thank you for that. I think it's more understandable than any live session we had so far.
Okay, great, awesome. Like I'm not a teacher. I'm doing my best. Like, you know.
Good job.
Yeah, so if it's helping, awesome. If it's not, I know what I can do. If it's not helping, this is my cat. He's really cute. You guys can just enjoy my cat.
I thought you were going back to bed.
All right. Go right back.
Dennis, you're awesome. May I have a comment about this problem, the way you solve it? Hello?
Yeah, please go ahead.
Okay, I wasn't aware how my mic is working.
That's
There is an alternative way to solve it, and it's more common way that I don't. So usually the most important assumption that I need to remark on here is usually you know what happened, you know the event. You know the what you're suggesting here to calculate the event, to calculate both the probabilities. Person A bought it, person B didn't, and then person B bought it, person A didn't. That in practice it doesn't happen. You know who bought, who didn't, and you calculate the posterior probability sequentially after each event. That's how you should address it in practice. I mean, in real life. When I say in real life, by the way, to give a little more of a context even, I've never had a lot of experience with complex calculations like that in business, in internet-related business, but rather they are used constantly in science, engineering fields, medical fields, trials, for example. When you have a clinical trial and you when you have a certain number of people going through the trial, and after each person receiving treatment and you observe the results of the treatment, you want to make sure you don't have to go through all the hundreds of thousands of patients before you make your decision. You actually want to update the probability that the treatment works or doesn't work as soon as possible, and then you want to stop the trial at the moment when you have a sufficient probability that you have your positive or negative answer.
Understood.
And so you don't. That's for the context. And so in that context, and usually in all the other engineering cases, etc., you have events where you certainly know what happened, and you have those events, they happen sequentially. Or even if they didn't, if they happened somehow simultaneously, you still go one by one. The way I solve this problem, and I'm sorry, I'm not going to be able to present any kind of awesome documents that you prepared, but the way I solved it is simply solved it for the first person. And I did assume, I think you said that it was kind of wrong or something, but I did assume that the problem was a continuation of what was in the lecture before. So I assumed that Maggie was the one who bought it. And so I calculate the probability for her, the posterior probability after the fact that she bought it. And then you take those numbers, and that posterior probability becomes a prior probability for the next event, which in this case is Meg, the guy, not buying it. All right?
Sure.
So as soon as you assume your state after the first event or after n event,
That makes sense.
that probability becomes a prior probability for n plus 1 event.
Does everyone
And
understand what
And
you're
that's
saying?
how you arrive at 60%. I'm not, yeah.
So what he's saying is that instead of viewing the two events the way I did, which is that not knowing, he assumed that Meg bought and the other one didn't, and then did basically the Bayes rule twice, right? Is that in essence what you're saying? So you
At this time, I'm not even at this time, I cannot even say whether the calculation is correct because the essence of the bias rule is that you know what happened, and that's why you update the probabilities. You cannot saying either that happened or that happened. I mean, what you've assumed here updates the probability because at least you have two people, and you have a 50% hit, so you know that.
Sure.
I guess. But in real life, for example, if I had a number of events that happened, I would certainly know what happened exactly, and it would probably even matter as to in what sequence it happened sometimes. But that's beyond the material that you're analyzing right now.
Sure.
Anyway, so Jess, I think it would be simpler if we all viewed this the way it's done in practice, at least as I've seen. And again, I may be wrong. Maybe there's some cases where it's tackled exactly the way you do. But I think it's easier. You have two events in this case. Just calculate for one event. In this specific case, we knew it was Maggie. If we didn't, we could just take person A bought it. Doesn't matter who that person was. And you calculate the bias rule with just one event, and then the result of that calculation becomes the prior probability for the person B who didn't buy. You understand? So the probability of good state given person A bought it becomes a prior probability for person B. So
Doing the Bayes rule twice.
yeah.
Yep.
Yeah. All right. I'll stop right there. I don't know if did that make sense to anyone else out there?
It is a great approach for the second problem, the robot problem. That's what you're going to have to. You're almost going to have to follow Leo's process.
Should we move on to the second problem?
Let's do it.
Yes, please.
Let me just give you another context out of real life, at least is where I've seen it. As somebody said, probabilities only start coming to life at big numbers. I don't know if you guys ever heard it, and I don't know. I honestly haven't heard 100% of Professor Lovo's lectures yet, but I don't know if he mentions it. But in real life, in real life applications, you don't do two events and then recalculate the probability of the state. So I think a lot of you in the cohort who commented, kind of asking what's the real application of all of this. I think that's how you kind of intuitively feel that when you're gonna start any business, you're not gonna like have two purchases and all of a sudden you make absolutely critically new decisions and out of those two customers, obviously. And that's called the law of large, maybe somebody will correct me, the right wording, the law of big numbers, I think it's what's called precisely. It's that to get the 50% probability, to get the observation in real life of half of the states being good, for example, or in this case, 60% of the customers buying your product, you don't go to 10 customers and get 6 customers buying. You go to like 1,000 or 10,000 or 100,000 customers, and then you approach the probability that you predicted, the 60% of those 100,000 customers buying.
Or you watch 150 robot races before you.
Yeah. So that's just a little context out of the real life. So our heads get confused with like, oh, we're now gonna calculate the probabilities after each customer in our real life buying our product or whatever. It doesn't really happen like that. But obviously you need to apply the same bias rule just 100,000 times. And this is what happens actually. In this case, we have 2 customers, but you would just repeat it 100,000 times in a real life observation and analysis. All right, I'm finished. Let's move on.
So luckily we don't have 2 events in the robot question. So we'll just follow through. And I basically, starting on page 11, use the exact same approach as was used for the previous question, which is start with our little trusty chart and start to map out the prior and the event. We read the question, and there's a lot of initial garbage about the island and the inhabitants, but it gets pretty juicy around I guess Tort requires returning or retuning every Friday. On the days Tort is retuned by Amenadine, who designed the robot, Tort has a 70% chance of winning. However, 1 out of every 4 days, she's too busy and her assistant tunes it. He only has a 30% chance of winning on those days. So based on that information, I use the same chart to fill out our information, and I guess I don't want to call it the trick, but the bit of logic that you have to use in this question to get to your probabilities of states is that if it's 1 out of every 4 Fridays, that means 70% of the time, or 3 out of 4 times, it's tuned by Amenadine, and 20% of the time, 25% of the time, it's not tuned by Amenadine. And to keep it within the context of the structure of the course, we'll call tuned by Amenadine the good state, and not tuned by Amenadine the bad state. I guess like everyone else is talking about in practical terms, I don't think it's actually referred to as the good state or the bad state, but just states. However, in this case, the course seems to be keen on using good state and bad state, so we'll stay with that in our chart. Now, if we use the chart and we get to that point, then we already know now one aspect of the equation we need to solve for the Bayes rule. And now we go on and we get our observation. And our observation is now that Tort loses the first race. So we know the probability of this in the good state. and we know the probability of that in the bad state. And it's a lot easier with one event that everyone can see. Okay. And so we now, by just using the chart and adding the events to the chart, we now have everything we need to solve the Bayes rule, or to use the Bayes rule. And so we come to the probability of 56%, which is a updated probability that she has tuned tort. That question is pretty straightforward if you use the chart. And I think that it's pretty easy to set up Excel so that if the chart is done correctly, then it's very easy to set up Excel to do the Bayes rule calculation for you, because it's the multiplication and division. So I'll probably create one that just has this all structured for you, and then you won't have to worry about that. But the math is right there on page 13 for that question. The third question is pretty similar. I didn't see much of a thing in it, so I jumped right ahead to the fourth question, which I think might have given some people difficulty, in that there wasn't a good state or a bad state in this question. That was obvious. There was 3 boxes of chocolates, and so you know, all of a sudden you're thrown for a loop, because this whole time we've been talking about 2 states, and now all of a sudden we're talking about boxes of chocolates. So I think the big thing to solving this question is, okay, saying, let's think of the box that we want to understand, box 1, which is the box that we want to know if he takes the chocolate from. So let's call that the good state. That's kind of the big jump that happens in this question. And box 2 and 3 together are the bad state. If you can mentally make that jump, then this question becomes quite obvious on how to solve it, which is that we're now looking for probabilities that you've taken something from box 1, or probabilities that you haven't. And probabilities you've taken a dark chocolate from box 1, or probabilities that you haven't. And so by organizing it that way, I think it makes question 4 pretty easy to understand on how to solve it, which is that we approach the prior from the point of view that the good state is the dark chocolate from box 1, and the bad state is from box 0. Maybe just a chocolate from, dark chocolate picked from box 1, or a dark chocolate picked from box 2 or 3. So it means you have to use the total number of chocolates to help you calculate some of the probabilities. And your probabilities of states are like 1/3, 1/3, 1/3, or because now we've lumped box 2 and 3 together, if you're just grabbing a chocolate, then there's a 1/3 chance it comes from, or a 33% chance it comes from box 1, or a 66% chance it comes from box 2 or 3. And that really is the sort of mental yoga that's needed in order to solve this question really easily. And that is my conclusion. So I don't know. I hope that really helps everyone. That really helped me sort of nail these questions using that approach. And what it is it's quite step-by-step and structured, so that it gives you at least a series of steps that you can use to approach these problems, as opposed to just having to fully understand the equation, if that makes sense. Boo! Yay!
Yes, it does make sense. It's just that I think the difficulty some of us that have no statistics background at all are facing is being able to understand it from this point.
Yeah.
Because I never thought of solving it this way ever.
Does this help at all?
Yeah, I'll just have to study this document a bit more.
This is by no means. I think some of the other people who were speaking earlier pointed out that they sounded like they had a much greater knowledge of the implementation of this stuff. This is by no means something for you to take and go out and then build robots with, or solve these complicated medical problems. This is very like laser focused to helping people get through these test questions that don't necessarily have the time or the statistical background to really dive in to the practical implementation of the questions. It's more just like a method that's hopefully will be as helpful to other people as it was to me. But I don't know if that makes sense. So I encourage anyone who's more knowledgeable to make themselves available to the cohort if they want to really drill down into building some robots together. I would like one that shoots laser beams.
Thank you so much for your time and all the explanations. I have to say, this is like very, very helpful, at least for me.
Amazing.
Same here.
I'm hoping to have something similar put together for week 2, because I know that that's really proving to be the challenging week. Week 3 and 4 are not so bad, but week 2 is really bad. So hoping some type of like a really disciplined, formal, step-by-step way to approach the questions in week 2. I think that should be helpful for everyone as well, if they're having trouble with this one. Is the net present value okay for everybody? I don't think it was that bad, but the nice thing about net present value. What's that?
I think the net present value is the easiest out of the entire course.
Yeah. Yeah, net present value, there's like a calculation in Excel that's just NPV. So that should really help everybody who's having trouble with it, because Excel does it for you. Yeah, great. Awesome. Okay, so thank you everyone so much. And
Thank you so much.
Yeah, please feel free to reach out like individually on Slack, and I'm happy to help as much as I can. I'm struggling as much as everybody, so I don't know. It's like I'm doing my best. I'm doing my best to help everybody, and you know, if it's not helpful, then find someone else. All right, thank you everyone. Cheers.
Thank you. Take care.
Thank you.
Bye.
Bye.
Thank you. Thank you.